and I will continue the tale about PhaseOne cameras. In fact, here you can see the main products. We have two series, IXU RS 1000, IXU 1000. RS two of the service series are different in lenses. The last system uses rod and stock lenses, which are much more photogrammetric, more metric lenses. They deliver better image quality, and these cameras use seamless technologies. New camera at the level of the camera itself, which can again be used for integration. This is this double camera, IXU RS 1900. It's 190 megapixels, and it's sold together with a system. You can buy a system specifically designed for it, DSM 400, with a stabilizing mount developed by Somaga, and the rest, I mean, the camera body was developed by PhaseOne. The control computer was also developed by PhaseOne, and on top you can connect any GNSS system. If you have GNSS system, IMU, GPS, I mean, you can connect the existing one. If not, then you can buy any other standard solution which is connected automatically. The solution, the second solution shown here, the Chinese UAV DJI 600, that the 50 megapixel camera is integrated with. For UAVs flying on small height, you don't need more than 50 megapixel. You can fly with this camera and monitor all sorts of size and observe different elements which were shown on the first slide. Here you can see some of the specs of the RS 1000 series. You can see a big set of lenses. You can buy any kinds of lenses available. All of them are metric lenses. If you need wide angle, low altitude imagery, or if you fly high, for any situation you can select the proper lens with different field of view. Of course, the lowest exposition in some models 2500. Even if you're flying with a CMOS sensor, which cannot take into consideration the image shift like in the previous technology, then considering that you have small high shutter speed, your quality will still be high because of no blur in the image, very high frequency of image acquisition. You can get one image of 100 megapixel every 0.6 seconds, which is 3 times higher than any other cameras available in the market. I'm talking about standard cameras like Eagle, Vixel or DMC. They have 1.6 second frequency. What does it affect? For instance, if you're into the development of 3D city models and you want to have many overlaps, the thing that I remember the question asked Professor Chibunich. It wasn't about that, but anyway, then you can get many overlaps, and as a result, improve the quality of 3D model. On a good speed, good altitude, you can have 93% overlap rate. You don't always need it, but you can have it with this cameras, especially it's useful for 3D city models. What else? CMOS, already mentioned CMOS. The pixel size is 1.4 microns. The size of the matrix is 11.600, which forms the overall 100 megapixel image. The images are done through central projection. You can get it processed with different software, even also photo mod. We have some examples of that. The weight, it's very lightweight if you use these cameras for integration. These cameras with any lens always weigh less than 2 kilos. There are some cameras with about 1 kilo, 2 kilos, but it mostly depends on the weight of the lens. And these camera bodies can be used on any kind of vehicles. This is a new product that was released just before InterGeo, just 2 weeks ago. You can see the live model right here. It has double lens of RS series mounted on it. This double lens forms, I will tell you later on how it forms an image, which again is a central projection image. And for that you can use any standard photogrammetric software that allows you to work with such images. The size of the image is 100 megapixel. The whole system weighs about 30 kilos. You can use it on lightweight airplanes like Cessna 172 or Cessna 206, 210, which have limitations on weight. That by definition reduces the cost of the flight in terms of the quality of the image and the metric parameters. This system is fully in line with the RS system. Now it is being tested in Israel, and if the previous has published its results on calibration and everything, the second one is being certified with the report to be published afterwards. So we have two lenses. Each lens has two sensors, and the sensors are shifted, one to the right, another to the left. Each sensor is 100 megapixels. The right sensor sees only the left side. Through the half of the lens it says only the left side, and the second left sensor sees only another half through half a lens. So they're shifted from the center of the lens. This way, at the bottom we have two images, each 100 megapixel. We can connect them. There is an overlap between them, and in this overlap, by known calibration parameters, these two cameras are simultaneously calibrated in this environment. We can connect them and get single central projection image. So based on two lenses, we have two vertical lenses, unlike DMC, for instance, with the oblique positioning, but sensors themselves are moved from the optical axis. As a result, we have vertical image, but with a broader field of view. That's how the system works. And so far, we have only one focal length, 90 millimeter, but because of this two images, we have quite broad field of view, 33 degrees if I'm not mistaken. The productivity of this system is about 63% higher than if we compare it with the new system with PhaseOne old system. For the same focal length, it's 63% larger, and time-wise, if we look at the 5 by 5 kilometer city, then with the new system, for the ground resolution of 5 centimeter, you need just 34 minutes to cover the 5 by 5 kilometer city. But if you want to use it for oblique imagery and 3D modeling, then in this case you'll have to do crisscrossing, that would be 2 times longer, and as a result you'll get all the necessary products with the 5 centimeter resolution. Now I'm moving on to the calibration program and testing program in PhaseOne in Israel. For that we developed a testing ground located actually not far from here. We're flying over this area quite often. This testing ground has control points, and the precision of control points is very high, 0.8 centimeters and 0.3 centimeters in their altitude, on their height. For that we specifically measured them using high precision GPS. These are constant control points, unchanging. You can see at the bottom what they look like, and they're well read on the images, which is very important for us. Generally speaking, on this section of the testing ground we have 53 such control points, and we can easily test and calibrate systems here by using airborne calibration. In fact, this is the testing process of the camera RS1000 with the focal length of 90 millimeters, for which we have published the report quite recently too, and we did a flyover parallel routes, 2 crisscrossing routes on the altitude of 2,500 feet with 4 centimeter ground resolution. Some parameters shown here. In fact, they're more like for your information, and in terms of precision they're not that important. We have had some parameters like the slopeness of the building so that we could put it into the system. We used Cessna 172, which we use for testing of all our systems, and we did used 3 configurations for accuracy calculation, 5 checkpoints and control points, and here we can see that we have 0.7 pixel and 1.5 pixels in the height. In height actually we can get even higher accuracy because we didn't use GPS here. We didn't use GPS here, that's why we have rectified it without GPS, and the height was jumping up and down here. That's why the accuracy was a bit lower than originally expected. I thought we'll get under such configuration about 1 pixel accuracy, but as a result we came with 1.5 pixels, which is quite okay. With a full centimeter ground resolution, to get height resolution of 6 centimeter is quite okay, which is fully in line with all the requirements and the demands of the grammatic instructions. So this is the next configuration, 9 points, ground control points, and we have a much better situation in height, 1.3 pixels and 15 points. We see that the GCPs, their number, do not affect, in this particular flyover, they didn't affect the planned positioning of the network, and the maximum accuracy in height was 1.1 pixels. That's what it looks like on the general slide. Here you can see 9 and 15 GCPs versus checkpoints, and as a photogrammetry specialist, I'm quite satisfied with this level of accuracy. Now let's speak about optical system. It's important for us to understand how this lenses in line with the standard calibration models.
That most of the software programs can account for in their functionality. Let's take Bingo. It creates a grid and then it can account for any calibration model. We say it should be brought to a certain standardized representation, because we know the camera distortion model, actually it's Brown-Conrad model that everybody uses. This is a model of the objective of the lens that was used in the flight. There is a distortion, it's symmetric, and it can be taken into account using specific coefficients. The second model is post-distortion. We can see some residual errors, less than 1 micron. The maximum line is not systematic, these are all random, and the maximum error is 0.91 microns. This is a good model to have and to work with. This is totally photogrammetric. When using extra parameters, you can achieve greater accuracy. For example, 0.68 microns, it's all in the report, but it doesn't really matter. When the residual error is 1 micron, I guess that's more than enough to do your task. In parallel, we're working with bench calibration, laboratory calibration. We visited Mi-Gaik recently for that purpose. We learned a lot of good stuff from them. So we have our own in-lab calibration system, which I would like to improve and bring it in line with international standards to make calibration processes stable, repeatable, and reliable. I hope it will help us promote the photogrammetric section of PhaseOne on the photogrammetry market and mapping market, and to take a proper place on the mapping market as well. Thank you very much. Any questions? So it's all clear, right? Alexander? Isn't there a bomb? Can I ask my question instead? I'm ready. About 190 megapixel camera. If I remember correctly, when Ultracam camera was designed, there were 4 lenses in one line, and there was synchronization by the shooting point, projection point. And the first DMC with oblique lens had a synchronization point that was not perfect. It wasn't a centrally framed camera. So they work at the same time, not from the same point. They are separated a little, but DMC also captured at the same time. Here we have 2 vertical lenses, but if it's a tall structure, the distance between axes is 5 centimeters, and CCDs are facing sideways, so each CCD captures half of the image. In DMC had a different system. They would take a full image of one side and then the other side. It was a different system altogether. Well, it's debatable. I will draw you a picture later. And the 100 megapixel camera the one that uses calibration report. So it generates a formula at the end. Well, it depends. There are 3 different systems adopted in the world. One Australis, USGS, and one other system, Photo Mode, supports all of them. And we generate all of them too. Now, can I ask my question? My first question, following up on the previous one, Andrei's question. At the end of the day, do you obtain an equivalent image? What's the focal distance? And the main point. I understand you eliminate distortion. We eliminate distortion at each image, resulting in an undistorted total image. So far the main point is in the middle. The distance in the air between them is 5 centimeters. 2.5 centimeters, no one will notice. What about focal distance? The focal distance will be based on calculations from 2 cameras. One, it's all combined. And about the polygon that you use for field calibration, what are the excesses? Excesses are very small. We can have large excesses, but it's impossible to make a polygon there. The pixels that I showed, the height accuracy or altitude accuracy was 10 microns, meaning that there were no excesses. That what do you use that testing ground for? It's not used for calibration, it's used for testing per se. Calibration takes place in a special room, so it doesn't matter if there are any exceeding points. It's best we check residual triangulation. I have a question about polygon. Do you have to create it yourself? How labor intensive it is? In shekels, you mean? Yeah, one way to do it. I can tell you how much it costs in shekel. 70,000 shekels. $20,000. So you don't have open data for polygons. Are there any requirements? If a similar testing ground is created in Russia, for example, so can we exchange these requirements with you? Sure.
When you buy one body with a few lens and you want to change them, every time you need to calibrate each lens for every flight?
Good question. I will answer. Okay. It is good question. Actually not. Actually not. We are not sure, I would say, currently about it, but supposedly, according to our manufacturing, we have not to do calibration, every calibration. Actually, you have calibration per lens, not per installation. Calibration per lens, not per installation.
But every time you have some changes.
Yes.
You're not sure it's in the same position.
It will depend if you're changing the lens for maintenance and then it's happening every $500,000, or just want to change between focal lengths. If you are looking on the 190 megapixel, it supports only the 90 millimeter lenses. So dual lens with 90 millimeter lens, you're not switching those. If you're looking on the single camera solution, we really have a range of different lenses. And based on our procedure, you need to recalibrate or doing metric calibration every time that you remove a lens, put a new one, and put it back.
No, wait, to translate without microphone.
Ah,
Well, maybe it's here.
okay.
Could you repeat it in a
Okay.
couple of words?
Okay, so just repeating the answer again. If we look on the 190 megapixel, the new camera, it's only carry one specific type of lenses. It's the 90 millimeter lenses. So the only time that you need to remove the lenses is based on maintenance that's happening every 500,000 activation of the shutter. So that's really depend on your project side, but it's taking probably more than a year. The second option is on a single camera where you have a choice or range of lenses that you can replace between them. Based on our production procedures, every time that you remove a lens from the camera and you put a new lens on top of that, you need to do metric calibration again. If you are an Israeli-based customer, we can do that in a very short cycle time. If you are living outside of Israel, then usually there is a local services by subcontractors or freelance.
One more question?
When you make IR triangulation with this camera, what is the expected accuracy of the triangulation in terms of pixel size?
Actually, it was presented in this.
Okay, you just tell
In this, it's about 1 pixel, less than 1 pixel and less than 1 pixel on position and about one pixel at height. But you have actually two parameters. You have one parameter, it's for aerial triangulation, okay? The second parameter is stereoscopic measurements. For stereoscopic measurements, it will depend actually on your focal length, on your forward overlap, all this stuff, because it actually forms your accuracy. We can predict your accuracy that you will get for stereoscopic measurements, okay? Because it is relatively easy to estimate, to calculate. Okay, we also have tested it for stereoscopic measurements. Actually, we took these images and we put them in stereoscopic measurement software like photo mode and measured 97 stereo pairs. 97 stereo pairs, and the accuracy was very high actually. But it is due to, we have, in this specific flight, we have large side overlap, large forward overlap, and we can choose actually different overlaps to produce stereoscopic measurements, okay? But in this case, it will be depend on your forward overlap actually and your focal length.